Hello, everyone, and welcome to the 2026 Statistically Speaking webinar series, which is brought to you by the Data Science and Analytics for Precision Rehabilitation Center and the Repro Rehab Training Program, both of which are funded by the Eunice Kennedy Shriver National Institute of Child Health and Human Development. This year, the focus of our webinar series is to equip rehabilitation researchers with principled, phase-appropriate approaches to sample size planning, from feasibility and pilot studies through clinical trials and effectiveness research. My name is Octavio Marin Pardo, and I'm today's moderator for this webinar. Our guests for this session are Dr. Christine Zainani, who you might remember from one of our previous discussions earlier this year, and Dr. Regina Nusso. Before I introduce Dr. Zainani and Dr. Nusso, I want to remind everyone to please mute your microphones for the first part of this session. In the event that someone is unmuted, please do not be offended if one of the hosts puts you on mute. So the first part of this webinar will be a presentation. And if you have any clarifying questions during the presentation, please put them in the chat and I can ask them when we have a good opportunity for that. And again, as a reminder, the initial presentation will be recorded and posted to the Dapper YouTube channel later. After the presentation, we will stop the recording and then open the floor for Q&A with Dr. Zainani and Dr. Nusso. During the Q&A, please use the Zoom feature to virtually raise your hands. And as the moderator, I will call on people one at a time. Alternatively, you can also post your question in the chat, and I can ask it as the moderator. So without further ado, please welcome Dr. Christine Zainani from Stanford University, and Dr. Regina Nusso from Gallaudet University, I'm hoping I'm pronouncing that correctly, who will speak about priori power, post-hoc power, and sensitivity analysis. Thank you so much, everyone, for being here.
Thanks for having us.
Yeah, delighted to be here.
I'm just going to share my slides. Okay, so we're happy to be here today. We're going to be talking a lot about actually post-hoc power and what's wrong with it and what you should do instead. A lot of you may have heard of post-hoc power before, but want to get into it sort of a deeper discussion of it's not just statisticians say not to do it. We're going to talk about why. Before we start, I want to let everyone know about Regina and I have a podcast called Normal Curves. And if you want to get some fun statistical learning, we talk, it's kind of like a journal club. We talk through papers, but we do it in a really fun conversational way. And we drop in some key statistical points, like what is Mendelian randomization? What is propensity, inverse probability of treatment weighting? What are the propensity scores? So it's a really great way to learn some statistics and how to think about research and paper. So I hope some of you will check that out. All right. Regina, I'm going to let you start by talking about what we're talking about today. First of all, with a priori power.
Right, a priori power. So I heard that some of you who attended previous webinar in this series learned all about a priori power, but I wanted to just show these three concepts and what questions they answer. So a priori power, given that I have not started my study yet, how large does my sample size need to be to have a good chance of detecting an effect that I already know that I care about? Okay, next one. Post-hoc power. This is what we're going to be focusing on today. Given that I got a null result, how likely was my study to have detected my observed effect if my observed effect were real? So if that feels a little convoluted, that's because the entire concept is convoluted. Okay, and then the last one that we'll get to today is sensitivity analysis. And this one is saying, given my actual sample size, given my N is fixed, what is the smallest effect that my study could reliably detect? And is that effect worth caring about? So they answer different things. They all have the word kind of power. They're all about power in here, right? A priori power is starting with this hypothesized effect size, saying, okay, I know what my clinically important difference is. What's my sample size? I need to detect that. Post-hoc power, yeah, go ahead, Kristen. It's starting with an observed effect size, and then it's talking about the chance of detecting it. And then sensitivity, you can already see kind of the logical convolution going on here. Sensitivity analysis starts with the sample size, and now it is giving reliably detectable effect sizes in here. So one more, Kristen. So these two, so good, we like these. Post-hoc power doesn't make a lot of sense, and that's what Kristen and I are going to talk about through a case study next.
Yes, thank you, Regina. That's a great setup for the case study that we're going to spend some time on, just because it's a really interesting case study because of the conversation that it generated. We're going to see that this resulted in a debate in the literature, and it's a fun. I actually think, Regina, that you and I should do a podcast episode on post-hoc power just so we can talk about this case study, because it's very interesting from a scientific process, scientific culture standpoint. But the study was published, it was a paper published in the Journal of Surgical Research in 2019, and it was entitled, "Is the Power Threshold of 0.8 Applicable to Surgical Science? Empowering the Underpowered Study." So 0.8, that's 80% power. And big picture, what they were trying to question or to have a conversation about is the 80% power that we all kind of know as the standard in the literature that we always seem to target, is that too big of an ask for surgical science? Maybe we shouldn't be targeting so high. That was kind of the gist of the paper. But now we're going to talk about the empirical evidence that they presented to try to back up their claim that maybe 80% power is too big of an ask. So let me just talk a little bit about what they did in the paper. So they spent some time. This was not they actually did a whole systematic review, essentially. So they reviewed 403 articles from Annals of Surgery, JAMA Surgery, and Surgery. So these are, I believe like the high impact target journals that everybody in surgery wants to publish. They were looking, this was a 2019 paper, so they went back a few years. It was 2012 to 2016. They went through all these manuscripts, and what they were looking for was they excluded statistically significant results where there was a positive finding or where they were missing information. They got it down to 16 negative studies. So negative study meaning I think that their primary endpoint was not a statistically significant effect. And it was mostly RCTs, very few observational studies. I guess, Regina, they do a lot of RCTs in surgery, perhaps?
Yes, I think they do, but I think this is where they're also getting very small sample sizes, as we will see, so they're more likely to have these negative results. So this is important, what Kristen just said. They excluded everything that had a p-value less than 0.05. They only kept the studies that failed, essentially,
right.
Only the failed studies, and they're analyzing. This will be important as we keep going.
Yes. So you can see they did a lot of work here. They went through all these papers, and then they had 69 studies. They probably, got a grad student some employment for some amount of time to go through these 69 studies. They extracted from these studies the effect size, the p-value for the main effect. Sometimes they, as we'll see, they averaged across more than one effect size. It's a little murky, but what the goal of this study empirically, what they were trying to calculate was they were calculating post-hoc power for the primary outcome of each article. This is the failed outcome. So they calculated post-hoc power, and then they presented that power in this chart here. And so how do we calculate post-hoc power? First of all, it's based on the observed effect size. So we compare the observed effect size to the standard error. We calculate a z-score. I'll go through a calculation in a minute, and that we calculate power basically after the fact, as I'll show you. So you can see the distribution. So we've got the calculated power. You can see that a lot of the calculated, what we call observed power or post-hoc power, it has multiple names that you'll hear in the literature. Wow, they're all really small. In fact, most of them are below 50%. And so they concluded, this is just, quoting from the paper, the median power in studies concluding insignificant differences was 16%, and only 4 studies made it to this arbitrary standard of 0.8. So again, this is leading to the conclusion, boy, 0.8 is just too much to ask. They did note in the results that 41 of the papers had actually provided an a priori power calculation, which is good. A lot of these were RCTs, so we're glad to see that they had done an a priori calculation. But I guess the authors were trying to say, ignore the a priori power calculation. That must have been wrong, because here's what we got for the post-hoc power. That's the gist of it.
So just to reiterate, just to reiterate that 16%, that 0.16 is saying, given the effect size that we already observed, what is the probability that we would have detected this if it were real? So just to get that 16%.
So assuming that the observed effect size is the true effect size, and then calculating power. I'll go through a calculation in a minute. Yeah. So they said, look at this. Oh, wow, this is all these underpowered studies. They were underpowered. And so high impact, this is their main conclusion, high impact surgical science was routinely unable to reach this arbitrary power standard of 80%. So the academic surgical community should reconsider the power threshold as it applies to surgical investigation. So they're saying, like, we got to rethink this whole thing, because we have empirical data that shows that all of these studies are underpowered, and it was way too much to ask to get them up to 80%. You might kind of be anticipating some of the flaws in the logic here. So first of all, what is wrong with their logic? So first of all, let me go through a calculation. So post-hoc power and p-values have a one-to-one relationship. So I can take any p-value and I can calculate post-hoc power, and no matter what paper it came from, no matter what the effect size was in that paper, the sample size or anything, given the p-value, I am always going to get the same post-hoc power, assuming the same alpha level, right? So let me just kind of go through the logic of the calculation, right? So power, again, is what is my probability of getting a significant effect given some assumption about what the true effect is. And again, this example, if we're assuming an alpha of 0.05, two-tailed, like sort of the standard in the literature, given any p-value, we're going to find the same post-hoc power. So you have to, we're doing two-tailed. So we say, what is the probability that we would have gotten a z statistic? And I'm assuming z here and not a t statistic just to make this simple, but like if we're on a standard normal, the cutoff for 0.05, as all of you may know, is 1.96. So we're saying, what is the probability that I would observe a z-value of greater than 1.96 if the true effect size is the effect size that we observed in this study? That effect size has been translated into a z-value. How do we calculate that z-value? We take the observed effect size in the study, in the observed standard error, we divide those, we get a z-value. So the effect size is expressed as a z-value, but that is just the observed effect size in the study. So we're saying, what if the true effect is the observed effect? We're going to assume that. Then what's the chance that we would have gotten a z-value greater than 1.96, meaning a p-value under 0.05? So just to give one example calculation, what if we saw in our study a p-value of 0.04? A p-value of 0.04 means that our z-value in that study from the observed effect size was 2.054, then you can just get that by going to a normal chart. So what is the power? We then calculate the probability that if you're on a standard normal, it's the probability that the z-value we're going to get in the study is greater than 1.96 if the true mean is the true z-value is 2.054. So we do a little algebraic rearrangement, and that translates to the probability that a standard normal random variable is going to be greater than negative 0.094. We're just subtracting the 1.96 and the negative 2.054. That turns out to be, if you go to standard normal chart, about 54%. We have to worry about the other tail, but the other tail doesn't contribute all that much. So it turns out to be about a 54%. So for any p-value, I can go through and I can calculate post-hoc power. It's always going to be the same given any p-value, again, assuming that we all choose the same alpha level. And Regina, you wrote an article about, actually, why don't you refer people to that article? It's really useful to read.
Right, post-hoc power is about what it is for physical medicine and rehabilitation, and it's talking about a lot of these arguments that we're doing today. And this was a figure that I had in the paper. So Kristen just explained how we are getting that one-to-one and how we are calculating that. Here I'm showing you, okay, across all observed p-values. So she picked 0.04 and explained how we get the observed power from that. This is across all observed p-values. What on this y-axis is the post-hoc power. And you can see that no matter what, again, given that we have this two-sided z-test and we have an alpha of 0.05, that small p-values will always give you high power. and they drop off sharply. Notice that curve, that is dropping off sharply. And then we see a p-value of 0.05 at the normal threshold, power of 50%. Interesting, right? And then we have this long, slow decline and big p-values, low power. So it's fascinating that they decided to only choose, the authors of the study, to only choose studies where the primary outcome had a p-value of greater than 0.05. So what they're basically doing is just saying, wow, look, everything to the right of, of that vertical dotted line, look, it's low power. But they could have just presented this this figure right here and not gone through all of the extra work that they did. I mean, prop to them for really proving it here, but we can also do it mathematically, and that's what we have here.
Yes. This is mathematically provable. And notice that p-value of 0.05, it corresponds to a power of 50%. Think about how the calculation we just went through, because you're saying, what's the chance that you're greater than 1.96? Right? If the observed effect is 1.96, the observed z value is 1.96, what's the chance of being greater than 1.96? If the true effect is 1.96, well, it's 50%, right? So in other words, every significant p-value, your observed power is going to be greater than 50%. Every insignificant p-value, it's going to be less than 50%. I'll just put a little plug in that Regina and I, for many years, wrote this column for PM&R, and we have lots of statistical topics there that you can go through if you want to learn about various types of regression. I have a lot about regression, data visualizations, different statistical techniques. So we have, that there's many, many papers, correlated data there that might be helpful in your learning. So again, post-hoc power is just p-value wearing a fake mustache. So it's just the p-value, right? So it has this one-to-one correspondence. And again, if the p-value is significant under 0.05, power is going to be greater than 50%. If it's not significant, it's going to be less than 50%. So if we go back to their results, all of a sudden we can realize, well, this is not surprising, and they didn't actually need to do a study. Right? This is mathematically inevitable. We don't need to do a study to show this, right? So because they actually only selected non-significant effect sizes, studies with negative results, of course, if you look at the primary outcome, the observed power is always going to be less than 50%. So it's just expected, and there was no reason to do a study. So right away, we're going to talk a little bit about, the authors got quite defensive about this. That's the kind of interesting story part of it. But right away, the whole premise of doing this paper was flawed, right? Because we don't need to do a paper. We know by definition that all non-significant results are going to be low-powered according to this observed power. What was actually the most interesting part of this whole thing to me as a statistician was, wait a minute, they actually had more than 4 studies. It was 4 studies above 80%, maybe 6 studies above 50%. How did they get 6 studies above 50% when the findings were not significant? I think what happened here, I'm not sure. Regina, do you have a guess?
Yeah, I did a little digging into this. I think it's because they only chose papers where the primary outcome was not significant, but then when they calculated power, they used primary and secondary outcomes, and they averaged them all together. So they had some situations where the primary outcome, so it was included in the paper, was not significant, but the secondary was significant, and so they muddied the waters. So this is even more confusing. Yes.
That is even more confusing, and thank you for doing that sleuthing, because I was puzzled by that, and I figured it might have to do with the averaging of multiple effect sizes, but I didn't actually dig to realize that they included the second. I was thinking maybe there were 2 primary outcomes or something. They included the secondary. Okay, interesting. So that is why this is a fascinating story. So yes, those are actually, that's the most surprising part of their empirical results, in fact. And it's weird, this whole averaging together doesn't make a lot of sense either. So I want to give some props to Andrew Althouse, because he is a statistician who saw this paper and actually took the time to respond on Twitter and then with letters to the editor, and raised concerns about the paper, that it should probably be retracted because in some ways it is silly. But I love the way, he's a very good writer, and I'm just going to read this because I think he just did a lovely description of the problems with this logic. So he says this approach is analogous to computing the mortality risk after a specific surgery by reviewing all cases of the surgery in question, discarding patients who survived. That's analogous to the studies that found a significant effect. Keeping the patients who died, those are the non-significant studies, and then concluding that the surgery is extremely risky because there was 100% mortality among patients who died, right? The analogy here is we took papers where the results were not significant, which is guaranteed to give you low power, and then we only looked at those are like the patients who died, and we said, look, low power is a real big problem in the surgical literature, right? Obviously, they didn't look at all the papers where there were significant findings, right? This is problematic. So he says the observed power is guaranteed to be low in negative studies, just as survival is guaranteed to be low if you calculate it only among patients who died. Therefore, the observation that nearly all studies with non-significant findings had low observed power is not surprising, nor is it meaningful. I really thought that was a very good way to put it. The interesting part is that this paper and Andrew's criticism and the criticism of other statisticians led to a special feature of the Journal of Surgical Research. So they did like a whole back and forth on this, which I found, I don't know about you, Regina, but I found really interesting because it shows why people are so wedded to this post-hoc power concept, even though statisticians have been saying not to do this for decades. So I found the back and forth extremely fascinating.
Yeah, so what I like about what the editor did for this, so this is the editor of the journal that had published the original 2019 paper, and that came under huge, blizzard of scrutiny on Twitter. And I admire him for saying, wait a minute, there's something here. He reached out to two statisticians to get their take on it. Should it be retracted? Does it, just need another comment on this? And they had nuanced takes on this. So he said, okay, this is how science works. Let's have this special issue where we're putting it all there. And I'm going to have these two statisticians give their analyses. And you can see that he's mentally struggling with the idea, the editor, because he's not a statistician. And he's saying, well, surely it's good for something.
Yeah, so it's interesting to go over what so the authors got a chance to respond to all of this, and it was interesting to see. It really gave some insight to me on why people are using this. Like, what do they think it's good for? So I found that very useful. So I want to go through some of the authors' rebuttals. So they got to respond to there were some critical papers, and they got to respond, as we often do with letters to the editor. So their first comment was like something along these lines. Okay, yes, we know that the p-value and post-hoc power are mathematically redundant. I don't know if they knew that ahead of time, but they certainly knew it after all of the criticisms and were at least willing to acknowledge that those are redundant. So they said, but wait, being redundant is not the same thing as being wrong, right? So they were saying, sometimes redundancy is not a bad thing. And basically, their argument was we need to repackage the p-value into this other quantity post-hoc power because readers are not going to make the leap themselves that, and by giving it in the language of power, basically, readers understand power, and it will remind readers that the fact that there was not a significant difference doesn't prove that the treatment and the placebo are not different, or the two treatments being compared are not different, right? So they were very worried about this idea. Non-significant results are sometimes misinterpreted as proof of no difference, right? And they said, hey, if we put the low power number, the 16% power in the paper, then a reader goes, oh, that might not mean that there's no difference between the treatments. It might mean that the study was underpowered. So it's like a reminder or a communication thing. Okay. All right. So yeah.
Well, I just wanted to give a hot take, Kristen, that I don't think that they are necessarily wrong here. I don't,
okay. Okay.
think that they're right or useful, but sometimes repackaging p-value into not post-hoc power, but it's something that we'll see later, but helping to remind readers that non-significant is not the same thing, that finding lack of evidence for something does not mean evidence for lack of something. So it's almost like they were on to something here, but then they lost the plot. So
well, yeah, we absolutely give them credit for wanting to remind readers and to communicate to readers that non-significant doesn't mean no difference. That is a mistake people make. So the intention is good here, right? That they're trying to remind readers there's lots of reasons that you would get a non-significant result that aren't necessarily that it's no different. So, okay, yes. And I think you and I, Regina, we spend a lot of time communicating things in different ways to try to get different points across. And sometimes saying something in two different ways can be helpful. So yes, I agree that being redundant is not always the same as being wrong. Now, my issue with this logic here is, again, as we've already said, low observed power is guaranteed in non-significant studies. So this study was providing no independent evidence that a study was underpowered, right? Again, it's just a mathematical thing. And my worry is that you rather than prevent, like the use of post-hoc power to get at this absence of effect is not, effective is not proof of that there's no effect, right? I don't think this post-hoc power helps readers, because what it might do instead is it might reinforce the belief that it might make them think, oh, the reason why we didn't see a difference in this study is because it was underpowered, and therefore really there is a real effect. Because in fact, power is defined as assuming that a real effect exists. So when you frame the result in terms of this language of power, you are actually kind of telling the reader implicitly that, oh, what happened here is a missed effect. We were assuming there's a real effect and it was missed, rather than reminding them actually it could be the case that there is little or no true effect. We don't know which, but it's favoring one explanation over the other just by calculating power at all in this way, right? And I like, Andrew did a really great job on this paper, I think. Definitely worth a read. I like how he tried to, I think it's great to explain things with examples. So he tried to make a hypothetical example to illustrate this point. I think he did a really good job. And he's saying, okay, imagine we have two trials and we're comparing two treatments, A and B. And in trial one, and they're exactly the same sample size in both trials, 1,000 patients. So the sample size is the same in both. It's not like one was smaller than the other. And imagine, though, in the first trial, we see a huge difference, 10% difference in mortality in the two groups. It's highly statistically significant. And we get, the post-hoc power correspondingly is going to be very high. But in trial two, we have the same sample size, right? So, I mean, in some ways, these two studies are powered to find the same real effects. They have the same power for a given set of real effects. But we go into the study and we see there's almost no difference in the two groups. By calculating post-hoc power, we're implying that trial two was underpowered and trial one was perfectly powered. But another explanation actually is just maybe the treatment does not work. The treatment given in trial two doesn't work. And so again, we don't want to refocus people so much on this idea that, oh, well, it could still be an effect, but it's just that it's underpowered, because it also could be that the treatment just doesn't work. So it's kind of forcing one interpretation on the data that may not be correct, right? So that's the problem, yeah.
Yeah, I think researchers often, when they think about power and sample size, they feel them to be almost equivalent. And
yes.
So when I review papers, I often see manuscripts saying, well, yeah, it's not significant, but that's just because it was a small sample size. And if I had just had a bigger N, then this effect size would have been significant. And they're overlooking the fact that if you had collected more data, that effect is probably not going to be exactly the same. So you can't have it both ways. You can't say, oh, I'm just going to, collect 10 people in each group, and then it's not significant, but it's this big, I promise. I'm just going to, if only I had money to collect more. So it doesn't quite work that way. Yeah.
Yeah. Regina, I love how you put this in your article on Post-Hoc Power, where you said this was a way of giving non-significant results an alibi. I thought that was a lovely way to describe it.
That was clever. It was clever.
Yes.
I didn't even remember.
Very clever. Yes. I love that. Yeah. Okay, so that's one. So the one argument is, hey, we need to repackage to communicate this idea to readers. So it's a communication thing. Their second argument was saying, well, but wait a minute, you're asking us to do something we can't do. So we don't really have reliable estimates of clinically meaningful effects in our domain of surgery. And here we have an effect size that we observed. So isn't that a good guess? Isn't that the best guess we have? So shouldn't we be calculating power based on this effect size that we happen to observe in this study? And they point out, a lot of times when people are doing a priori power calculations, they do reach to observed effect sizes in the literature. So then why can't we do this after the fact? What's wrong with this? So the problem with their logic is, as Regina was just alluding to, the observed effect size is itself an uncertain estimate. So you can't just pretend that the observed effect size is the truth. And that's what they're doing when they calculate this post-hoc power. They're saying, hey, we saw this, so this must be true. And in fact, there's so much uncertainty in this estimate that people have done simulations. This is a really nice paper from General Psychiatry where they did a bunch of simulations. And they're saying, hey, if the true power, of course, when you do a simulation, you get to actually know the true power. You don't usually know that in the real world, but in a simulation, you can say, we know the effect size, and we know that the power in this study design is 45%. So that's the red line in the middle here. And they're saying, let's actually now simulate 1,000 studies where the true power is 45%, and let's see what the post-hoc power is. And it turns out the post-hoc power is all over the map. So you can see that if I did this study over here, I would think that the post-hoc power is, almost 1. And if I did this study over here, I happen to get this study, and it might be 10%, and it's all over the map when the true power is 45%. So it's not a good estimate of the true power to just use this observed effect size and calculate this post-hoc power.
I think sometimes people fail to appreciate the subtle point that every time you take a new sample, you're going to get something different. And if your population has a lot of variability in it and you're getting, a small sample, then it's going to be wildly different all over the place. That sampling variability, I think we don't have a good gut intuition for. We're like, yeah, it's going to be a little different. No, it can be wildly different, which is what we just saw on that previous.
Right. Especially with smaller effect, when your sample size is smaller, it bounces around quite a bit. One more note on post-hoc power. This is a little bit more philosophical, but Regina, I grabbed this. Sorry, I stole this from your paper because that paper is so good. It's just a really good thing to think about. So post-hoc power analysis, it's philosophically wrong, right? After you have actually already done the study, there is no probability, right? You either got a significant result or you didn't, and your result is either a false negative or it's not. There's no probability anymore associated with that event. So this is why we distinguish between pre-study and post-study probabilities. So that's why we might use a previously observed effect size to do an a priori power calculation ahead of a study, because that makes sense because there's still probability associated with it. But once the study is done, it either was a false negative or it wasn't. It's 0 or 100%. There's no power really in the traditional sense. I love what you put here, Regina. You said, before the coin toss, the chance of it landing heads are 50%. After the toss, it's heads or it's not, right? So observed power is like looking at the results of a dice game and using that to calculate the probability of winning. It's after the fact, yeah.
Okay, so let's talk about sensitivity analysis then. I think of this as what post-hoc power wants to be when it grows up. Like, I feel like these poor authors, they were on to something, like I said, but I think they lost the plot. I'm not sure that maybe anyway, I can't imagine what they were thinking. But this idea where they said, we're just going to throw up our hands because in surgery, we don't know what a clinically important difference is. Like, who knows? You're testing these new surgical things. So therefore, let's just give up and let's just use this observed effect size that we saw here. Bad idea. So I think what they were groping for, not knowing this existed, sensitivity analysis, and it's really just kind of a reframing of the idea. Now that your sample size is set, what's the smallest effect that you can reliably detect? So before we were saying, okay, I have a minimally clinically important, difference in mind. What sample size do I need for that? And I think that's what you all learned in a previous webinar where you're doing simulation-based approaches to this. This is
Aaron's
the other
talk,
way.
yeah.
This is right. This is saying, okay, you've got your N. Now, maybe your N is set because you've already done your study. Maybe your N is set because that's all you can afford. Sometimes we've got logistics in here, right? I mean, let's be real. Or you ran out of time. You need to graduate. All of these things are real. Okay, now that I have my N, what is the smallest effect I can reliably detect And is that effect even worth caring about? Like, what did that effect mean? So it's kind of flipping it around. So next slide. Right. Okay. So I loved Andrew's example. So I'm going to take these two trials and then say, okay, this study design, notice this same study design, but two different results. So this study design, what was it powered to detect? What effect sizes could I get from this? And it's, okay, so we can make this nice graphic here. Let me walk through a little bit of what's going on here. So the x-axis is the effect size. Oops, if you can go back.
Oh, yeah. I don't want to give it away.
Well, I just want to set up kind of what's going on because it can get a little busy. So that x-axis is talking about the effect size here. And since we were talking about two studies and mortality difference between them, and I think the original one was 50% in the control group and 40% in the treatment group. And instead of working with 40 and 50%, I just changed these to percentage points. So this 0 percentage point where you see this, this vertical line, that's where the treatment group was exactly the same as the control group, where there was no difference. And that's why you have that 0 there. Everything to the left is where the treatment group was better because you had reduced mortality. Everything to the right is where it was worse and you had greater mortality in the treatment. And remember, this is a two-sided test. This is what we do in statistics. So we have to look at both of these. And that's what's going on here. Now on the y-axis, I have statistical power here. So not post-hoc power, but this is that before I've even looked at any results, the statistical power for each of these specific effect sizes. Okay, so we've got that. So we've got 100%, 0% down there. All right, next one, if you can do that. Okay, what do we have going on here? That 80%, that is what we have as a typical goal, right? 80% chance of catching a real effect of a certain size if it's really there. So you can play this game. It's almost like this chart gives you, this figure gives you a lot of room for discussion. It's very meaty and interesting. So you can, look at this slice wherever. You can say, okay, we're okay with 50% power. We're okay, we really want to have 90% power, whatever it is, but we have 80% power. Okay, if I want to tell everyone that I have 80% power, 80% chance of detecting a true effect, what is that minimum true effect that I am powered to see, right? How much power do I have? And that's when you're going down to the effect size down at the bottom. And it ended up being 6.3 percentage points here. So this is, and then everything. So the shaded bit that I have going to the left, that is the range of effect sizes. So remember, that's just the minimum. It's easier to detect a bigger effect size, but that's the minimum that it can detect is 6.3 percentage points. So, 50% compared to whatever, 44%. But if it's bigger, if the mortality were even lower than that, that's fine. That's good. We can do that with 80% power. It's getting smaller that's getting harder. So this can be done at any point in the study. And what I like about this is that it reframes the questions. Would a reduced mortality of at least 6.3 percentage points be clinically meaningful? Maybe that's too small. You can start to talk with, your readers or your colleagues and say, maybe that's important. Maybe it's not important. What is the background? What do we care about? All of this. And yes, there's no one right answer here, but that's where science comes in. The statisticians can't tell you the answer. You have to, at some point, bring in the scientific knowledge here and talk about, okay, what really makes a difference? Then you have to ask the next question. Okay, is it a plausible range? And I'll show you what I mean for that in a minute. So this is, I think, very interesting. This is the sensitivity analysis, is looking at this. Notice that this is very different than reporting post-hoc power. This is focused.
Regina, I feel like this is what the authors of that paper should have done, right?
Yes.
Taken all the papers, significant or not, and then calculated this, minimal effect that you could find, and then said how many of those would we care about, right? Like, did we have 80% to actually 80% power to actually detect a meaningful amount. And maybe it turns out they only had 80% power out of all those studies to detect clinically meaningful effects in a very small handful. That would make their argument that 80% is too high of a goal. But they didn't. This is what they should have done, not what they did.
They were dodging responsibility, I think, here. Okay, so next slide. This is, if you really, really, really want to work backwards, like Christy and I've been saying, no, don't do that. But you can. But if you really need to, then remember, Kristen talked about 2 studies. So this study 1, trial 1, that had what it was. What was it? It was 40 compared to 50%, right?
Yeah, 40% and 50%.
Right. That's where that green diamond is.
Yeah.
And so we can see, it was nearly 100% power, right? Anything 40% mortality or below, 10% improvement or more. Well, that we're like pretty much guaranteed to see that, because that's huge. So we can do the same thing for trial 2. Next slide. Where you had an effect size of 0.1 percentage points, right? It was 49.9% versus 50%, something like that. Okay, we're only going to have like 5% power here. And that 5% is only because we have an alpha of 0.05. We're going to, this is as minimum as you could go. So this is answering that same question, but it's showing where it all falls along on the same curve. So next slide. That was with 1,000 people per group. Let's do this. Oh, go ahead.
No, go ahead. Yeah, no.
Okay, yeah, okay. So let's do the same thing now with 100 in each group. So same deal going on. We need to find that 80% power, because that's what all the reviewers want. That's what scientific establishment expects. What is that minimum detectable difference? It's a 19 percentage point reduction. So this is the point where you say, okay, would this be meaningful? Before we had a small difference, so we have to say, okay, is this how important is this? This a 19 percentage point reduction. Okay, that's big. Is it plausible that we're going to find an effect this big? I think Andrew in his paper said, okay, that's going to be like a life-saving thing, and we probably would have already discovered it. 500
yes, exactly. Yeah.
If we were able to get that big of an effect there. But this is good. If you do this ahead of time, then you're able to say, ooh, maybe it's not even worth us doing this entire study because we are only powered at our desired power of 80% to see something that's so unrealistically large that we're not going to get what we need out of this. So we're probably not going to get significance.
And Regina, I think doing this after the study does have some value as a post-mortem.
Yes.
So let's say you forgot to do, remember in the studies that they looked at, 41 of them did have an a priori power calculation. But let's say you forgot to do one, or and you did, or somehow you got it wrong. You can do this after the fact. I think this is what they were trying to do is and then you can say, oh, whoops, we didn't plan this well because our study really wasn't powered to find anything clinically meaningful. But notice it has nothing to do with the observed effect size. This has to do with how the study was designed. What was the sample size, not with what observed effect size we happened to get in the study.
Right. And then, of course, now we can go even further down to, I think, what did it do? And at 50, right? Like, okay, at that point, don't even bother.
Don't bother with the study, yes.
Right. So this is essentially a restatement of the things that we've been talking about before. But as Christy and I said, sometimes restating things in useful ways it can be helpful to be able to see this this continuum. The problem sometimes with power calculations is that we want to make everything discrete. Okay, one effect size, one 80%, one, and no, it's all it's a system, a very complicated system. So let's start looking at the relationship between all of these and see if that can lead us to meaningful discussions.
I think probably Aaron Caldwell in his talk, in showing how to do simulation for a priori power, I'm sure showed a lot of power curves. I always prefer a power curve. She shows the whole thing rather than just picking one arbitrary number, because that's not going to be a very good representation of the truth. All right, so I think that kind of wraps our discussion. We want to have plenty of time for talking and for questions. Again, I'll remind everybody to tune into normal curves. We are talking in the episode just released and the episode next week about if you are paying attention at all to the Gallery cancer blood test. It was a big thing in oncology. I don't know if because you guys are not in oncology, you're paying attention, but anyway, just some big data came out on that. So that's a fun one to listen to. I will give a little plug for one of our sponsors, which is Graph2Table. So if you have to do any statistical sleuthing, this is amazing AI tool. You just pop it. If you've ever used Web Plot Digitizer, no more Web Plot Digitizer. This is way easier. You plop the figure into Graph2Table, and it's an AI powered, so it automatically extracts everything, no work involved. And we have a discount. So if you put normal curves 20 in, you get a discount on that. It is a paid service, but unlike Web Plot Digitizer, but it will save you so much time. It's worth paying, but you can use our discount code.
I just want to say I've never seen Kristen so excited.
If you have ever had to use Web Plot Digitizer, which I have used so much in my life, and you have to go and click on those individual dots and put the axes, and it comes a little different every time. You will be so enamored of.
I was skeptical, but it is useful, even if you're not doing statistical sleuthing. I
do a lot of statistical sleuthing, clearly, but for systematic reviews and meta-analyses, often very useful. Right, yeah. And also, Regina and I do a lot of teaching. So I've mentioned the PM&R Statistically Speaking columns. We have those going back to what, 2007, 2008, maybe?
Oh, yeah, it's been a while.
It's been a while, so there's lots of topics, and we have one on principal components analysis. Regina just gave the graduation speech for the statistics department at Stanford. And I loved her speech because she made a metaphor with principal components analysis. So I've told her we're going to have to do a normal curves episode on principal components analysis and have her give the speech because it's so lovely. So I have a column on principal components analysis, lots of one-off topics that you can learn. We also teach, I have a whole medical statistics certificate program that's quite deep if you really want to go deep and do a lot and get up in your game in statistics. Regina and I also do one called Demystifying Data, which is more of a gentle introduction. If you want the gentle introduction to statistics, we really focus on intuition and concepts as opposed to formulas, applications. So that can be very useful for applied scientists. And then we teach a whole course on clinical trials. And so if you're going to be participating in a clinical trial, it's very useful for the sort of the nuts and bolts of clinical trials. So. All right.
Welcome questions, discussion.
Yes, I will stop my share here and we can open it up for questions that you guys may have.
So before that, thank you so much, Dr. Zainani and Dr. Nuso, for this. It was a very interesting topic and very enlightening as well. So for all of those of you in Zoom, please, if you have the time, please scan the QR code. I'm also going to put the link on the chat in a few seconds to share your feedback about this session so that we can improve it like for the future. And don't forget that our next session, actually a short announcement as well. We're going to take like a short break during the summer for these webinar discussions, but then we're going to continue in September. So please be sure, like you already are subscribed to these webinars, so no need to RSVP again. But if you share these webinar links with your colleagues, then please let them know that we would need you to RSVP. Anyways, so thank you again very much, Dr. Zainani and Dr. Nuso. I will now stop the recording and open the floor for the Q&A portion.